Hi everyone, in this video I'm going to be going over the answers to the quiz review. So, starting with number 1, electron domains. I'm not going to write out the whole answer, but basically an electron domain is either, let me get my pencil, is either a bond, and that would include a single bond, a double bond, a triple bond. Each of those would only count as one electron domain. Or a lone pair of electrons. And we'll see in number 2 the examples of that. So it says how many electron domains are on the central atom of each of the following molecules. So for this first one, we have 1, 2, 3, 4 bonds on the carbon. So that has 4 electron domains. This one has 1, 2, 3, because for electron domains, a double bond still only counts as 1. So 3 sort of groups of electrons on the carbon. So this one has 3 electron domains. This one has 1, 2, 3 bonds and a lone pair. So it has 4 electron domains. And then if we break it down into lone pairs or bonding domains, this one just has 4 bonding domains, because there's 4 bonds. This one just has 3 bonding domains, and then this one has 3 bonding domains and 1 lone pair. Okay, and now explain why NH3, and let's just redraw that here, is shaped kind of like a pyramid instead of a flat triangle. So in other words, why is it not shaped like this, with the H's all spread out? And the reason for that is this lone pair of electrons. Electrons repel other electrons, remember, and bonds are made of electrons. So this pair of electrons is pushing away the bonds with the hydrogen. But you can't see the electrons in the actual molecule, so you just end up with a molecule that's shaped like a pyramid. Again, because these electrons are up here pushing down those hydrogens, pushing them away. So it wouldn't be shaped like this, because then we'd have these electrons here and these bonds would be too close to the electrons and they need to push them out. The next one, what shape would we expect the molecule over here to have? So we would not expect it to be a straight line shape like this, because again, there's this lone pair of electrons that's going to push these bonds away from itself. These negatives repel negatives. So we would actually expect the shape to be more like this, a bent shape, or sort of a V shape, to again, spread out those electrons as much as possible. Right. Next, the concept of electronegativity. So electronegativity is how much an atom attracts electrons. So how strongly an atom attracts electrons to itself. The general trend for electronegativity, if this was a periodic table here, is it increases as we go this way. So this would be the least in this corner of the periodic table, and this would be the most in this quarter of the periodic table, except this last column, the noble gases. Because the noble gases already have all 8 electrons. They don't want any more electrons, so they don't attract electrons at all, even though they're over on this side of the periodic table. So if we look at which atom is most electronegative, it's the one that's right up here in this corner next to the noble gases, and that is F, fluorine. Fluorine is the most electronegative atom on the periodic table. So if we're putting these in order from most to least electronegative, we already said fluorine was the most, so that's going to go first. Oxygen is going to be next. Oxygen is next to fluorine. We draw this again, like here's fluorine, there's oxygen, next one over. Next one over is nitrogen, and then carbon. So carbon's going to be next. It's not very electronegative. But argon is a noble gas over in this noble gas column where they have no electronegativity, so argon has to be the least electronegative of those. Okay, and in this question, in covalent bonds, electrons are shared. What happens if two atoms are bonded, but one is more electronegative than the other? So let's consider like oxygen and carbon, for example, two of them from this example. Oxygen, carbon, and they're sharing 2 electrons in this bond, right? But oxygen is more electronegative than carbon. So what's going to happen is oxygen is going to pull those electrons in that bond closer to the oxygen. So maybe they're kind of like that, closer to the oxygen and further from the carbon. It's not able to take them completely, but it's going to pull them closer to itself. And then what happens is this oxygen ends up being kind of negative, because remember electrons are negative, and this carbon ends up being kind of positive because it had its negatives pulled away from it. So now, if we call a molecule polar, that means that it has a partial negative side, one side that's getting the electrons more, and a partial positive side, one side that's getting the electrons less. And again, this is due to the electrons being shared unevenly. Remember, the protons are stuck in the nucleus of the atom. Protons aren't going anywhere, but the electrons, those are able to kind of move around. So those are the ones that are going to be shared. Generally in a polar molecule, the negative side is the side with the most electronegative, because again, electronegative means it attracts electrons. It's attracting those negative charges. So if you're trying to decide which side of this molecule is positive and which side of this molecule is negative, look for where is the most electronegative atoms in that molecule, because wherever the most electronegative part is, that's going to be the negative part. If a molecule is the same on every side, that molecule should be nonpolar. So if it's symmetrical, if it's got the same thing sort of on every side, no side is different from another side, then the electrons are going to be shared evenly, so that ends up being nonpolar. What would we expect to dissolve in water, a polar molecule or a nonpolar molecule? Well, water, H2O, here's O and H and H, is shaped like this. So water is a polar molecule. The oxygen is more electronegative than the hydrogen, so we have a negative side here and a positive side here. And there's a rule that says like dissolves like. So polar stuff dissolves in polar stuff, and non-polar stuff dissolves in non-polar stuff. So we would expect, since water is polar, a polar molecule should dissolve in water. Like sugar, for example, is a polar molecule. A non-polar molecule, like oil, should not dissolve in water, because like dissolves like. So here's some examples of molecules. We're going to classify them as polar or non-polar, and then write in the partial charges if they are polar. So this first one here is polar. This one right here is non-polar, and this one right here is polar. Now, how can I tell? This molecule has 2 different sides, this first one. It's got the side with the nitrogen on it, we put a dotted line here, and it's got a side with the hydrogens on it. 2 different sides, that makes it a polar molecule. And the nitrogen is more electronegative than the hydrogen, so the nitrogen side is negative, and the hydrogen side is positive. Now, I'm not going to put a little positive on every hydrogen, because with polar and nonpolar, we're just looking at the different sides of the molecule, not each individual atom. This next molecule right here is nonpolar, because every side is a chlorine, right? All 4 sides are chlorines. I can't draw a dotted line somewhere dividing it in half and have 2 sides that are different. So these chlorines are more electronegative than the carbon, but what happens is if you have a chlorine here pulling this way and a chlorine here pulling this way, and they're pulling equally hard because they're both chlorines, the electrons don't go anywhere. It's like a tug of war where you have two people who are equally strong on both sides. The rope doesn't move. Same over here. This chlorine's pulling this way and this chlorine's pulling this way, opposite directions. It's a tie. So the electrons just stay where they are, evenly distributed. This last one is polar because we do have two different sides. We have a side that has an oxygen on it over here, and then we have a side that has no oxygen on it over there. Now, if I'm trying to decide which is the negative side, if you imagine this molecule, you've got two chlorines that are pulling in opposite directions equally, and then you've got an oxygen that's pulling this way with nothing pulling against it. So this oxygen is going to be able to attract more electrons. Also, the oxygen is the most electronegative atom in this molecule, so this ends up being my negative side, and the opposite side ends up being the positive side. And finally, intermolecular forces. Intermolecular forces can generally be described as how much molecules tend to stick together. So again, intermolecular forces are what we're talking about if we have a bunch of molecules together in like a beaker or a droplet or something. How much do those molecules tend to stick to each other? The weakest intermolecular force is dispersion. So it says order from weakest to strongest. So dispersion would be first as the weakest. Dipole-dipole is in the middle. And then hydrogen bond is the strongest kind of intermolecular force. The only intermolecular force present in non-polar molecules is dispersion. So if you've got a non-polar molecule, that is the only force causing it to stick together, and that's the force that's just caused by the random movement of the electrons, and maybe just randomly more electrons end up on one side, and so that side ends up negative, and then the other side ends up positive, and maybe they can stick together. But it's pretty weak, it's pretty temporary. True or false, intermolecular forces are real bonds which require a chemical reaction to break. That is false. So they are forces, they're not actual bonds. They're sort of a temporary sticking together, but they can be pulled apart without a chemical reaction. They're not as strong as real bonds. So dipole-dipole and hydrogen bonds occur when the negative end of one molecule is attracted to the positive end of another. Because remember, with polar molecules, like we can do water again, you have a negative end and a positive end. So if I had two waters, H, negative, positive. This hydrogen end that's positive would be attracted to this negative end with the oxygen, and we would have an intermolecular force that would cause those to tend to try to stick together. If you have a polar molecule, how can you tell if the intermolecular force is dipole-dipole or hydrogen bond? Hydrogen bond, again, is just a stronger dipole-dipole. It's a dipole-dipole when you have a really big difference in electronegativity between the two, between the atoms in a molecule. So you get a pretty strong partial positive and partial negative. Hydrogen's bonds form when you have hydrogen bonded to oxygen, or hydrogen bonded to nitrogen, or hydrogen bonded to fluorine. So if you see that pattern in a polar molecule, you know that molecule should be able to form hydrogen bonds. If you don't see that, but it is polar, then it can form dipole-dipole, but it cannot form hydrogen bonds. Don't think just because it has hydrogen in it, it can form hydrogen bonds. It has to be hydrogen, again, bonded to oxygen, nitrogen, or fluorine. So identify the strongest intermolecular force present in a group of each of these molecules. So if I'm trying to do that, first thing I need to do is determine whether the molecule is polar or not. So this one is polar. This one is non-polar because it's symmetrical. It's got the same thing on every side. And this molecule is polar because it is not symmetrical. It's got different sides. So for the nonpolar one, the only force it can have is dispersion, because it doesn't have a negative end and a positive end. Then for the polar molecules, I have to look, do I have hydrogen bonded to oxygen, nitrogen, or fluorine? In this molecule, I do not have that, so the strongest intermolecular force for this one is going to be dipole-dipole. In this molecule, I do have that right here. I have an oxygen bonded to a hydrogen, so the strongest intermolecular force for this one is going to be hydrogen bond. Okay, now we're going to look at this molecule above, and we're going to show how they would line up if we had a big beaker full of these. So I'll draw one of them. And if I'm trying to figure out which is the negative side of this and which is the positive side of this, phosphorus and chlorine are in the same period on the periodic table, but chlorine is further to the right. So we expect chlorine to be more electronegative than phosphorus. These two chlorines are pulling in opposite directions, but this chlorine is pulling up, not as harder than the phosphorus is pulling down. So we would expect this side to be negative and this side to be positive. So when we line up two of these, here I'll draw another one in a different color, we would expect them to line up like this, with this phosphorus next to that chlorine, because this positive side and this negative side are going to attract to each other. And then finally, the effects of the intermolecular forces. We expect a molecule with stronger intermolecular forces, like say hydrogen bonding, to be harder to evaporate. And another way of saying that is that it has a higher boiling point. If you compare things like water and rubbing alcohol, water has stronger intermolecular forces and it will evaporate a lot slower than the rubbing alcohol would. That's good for us because we need liquid water to survive. So it's good for us that water doesn't evaporate very easily because of its strong hydrogen bonding and intermolecular forces. In general, we also expect a molecule with stronger intermolecular forces to be thicker. This also depends on the size of the molecule in question, but generally stronger intermolecular forces will be more viscous or thicker than something with weaker intermolecular forces. And finally, we expect a molecule with strong intermolecular forces to be more likely to be a solid than a liquid, and to be more likely to be a liquid than a gas. So it would freeze at a higher temperature, at a warmer temperature, than a molecule with weaker intermolecular forces. Again, because the molecules want to stick together, so it's easier to get them to stick together in a solid. It doesn't have to be as cold as it would for a molecule with weaker intermolecular forces. It's harder to get them to stick together into a solid, so it'd have to be an even lower temperature and be colder in order for them to freeze. Okay, so that's the end of this review. Please message me if you have questions, and good luck on the quiz.